So this is the idea of the way this ride works, and this is when the ride is spinning at omega. So some speed. The simple thing about this ride is that you really don't need the rotational motion stuff to do this problem. This problem can be done with traditional net force that we talked about first semester. But there's clearly a rotational component related to this problem. And if you approach it from the standpoint of rotational motion, you may end up being disappointed in what you can do and what you can't do here. I bring this up because if you're not careful and you start down the road of treating this using rotational motion, you may get yourself painted into a corner. And the reason is because moment of inertia. If we assume that the person before we start has is a point mass at the bottom of this ride, and their moment of inertia is based on how far away from the axis of rotation they are, then there are 6 people, each a distance a away from the moment of inertia. The moment of inertia of the system is 6 ma squared. Oh, Jesus Christ. That also means that, I don't know if you see this, but can you imagine that the faster you spin this, the more the people swing outwards? So this has a moment of inertia that is a function of omega. Because the faster you swing it, the more the people will swing outwards, and that will change the moment of inertia, which will mean that the harder it is to turn this changes as you turn it. This has a name. It's called a governor. It's a system that makes it more difficult to move an object the more it's being moved. And they use governors in all sorts of things. If you've ever been in a vehicle that is governed, that usually means that it's designed in such a way to have a maximum speed or a maximum RPM or some kind of maximum range, and they use governors to do that. This is a simple, straightforward, what's considered to be a mechanical governor that would govern how much, change in velocity you can accomplish based on the way you spin the object. You don't have to do any of that for this problem. But I think because it's a rotational motion problem, people tend to feel as though this is the way to go. There's an easier way to do this problem. And I put it in this homework because when you're faced with the AP exam, the thing that you have to start to come to grip with is that you're going to get a whole bunch of problems thrown at you, and you're going to have to decide on the fly what is the best way to address that particular problem. And you won't necessarily know whether you should use rotational motion or circular motion or not. This problem can be done lots of different ways. It's pretty much open for interpretation. Let's start with part A. It says that draw a free body diagram for rider X under a constant rotational condition to part 2 and clearly define any symbols you introduce. I think that's pretty easy. As it's rotating, based on the direction I have it indicated, the person's only experiencing 2 forces. Weight downwards. Not sure how straight down that looks, but... and tension upwards. Those are the only 2 forces they experience. They don't experience a sideward force. Once it's spinning at a constant speed, they don't have to have a speed to keep them moving. So they only have to have that speed to get them started. They need an unbalanced force towards the center because each person is traveling in centripetal motion. So when we look at this tension, part of that tension is causing an unbalanced force towards the center, so they travel in a circle, and part of that force is keeping them from falling to the ground. And that's important because I am pretty sure that the faster this thing goes, the more force is going to be required towards the center, which means this tension increases as they go faster. The smallest the tension will be the weight of the person, but the greatest it'll be, spin it faster and faster and find out. Question B, derive an expression for omega in terms of everything else. So that's kind of an interesting thing. We want omega in terms of other things that are here. You'll notice that what's missing from that list is the tension. It's not a part of this list at all. But let's use the fact that net force is equal to MAC. Again, like I said, this problem could be done from the standpoint of torque, but I think this is the right way to go. I think it's faster. we only have to deal with one person. We don't have to deal with all six, because we only have to deal with the forces acting on the one person to do this problem. And that's what part A is about, cluing you into just looking at one person. If part A wasn't there, you might look at the whole system at once instead. There's only two forces that I have to worry about. That's going to be T sine theta, because that's the only one that's in this direction. That's T sine theta. And that's going to equal MAC. Now, I know T can't be in my answer, so I'm pretty sure I'm going to need net force in the Y direction eventually, and that's going to be 0. And for that, we'll have T cosine theta equals mg. Just going to tuck that away for a few minutes. AC is omega squared times R. So I'm thinking this is how we work omega into the problem, is through its connection with the centripetal acceleration. That gives me T sine theta equals m plus u omega squared times R. But R, do we want to handle R now or later? We should handle it now. R is this distance. That's going to be equal to A plus L sine theta. Any question about where I got that from? All righty. So A plus L sine theta. Now, I'm going to remember that from last year or last semester. If we have a sine theta and a cosine theta term, line them up and divide, just get the tangent. I think that works here too. Cancels the m's out, and I get omega squared over g times A plus L sine theta. And all we actually need is omega. So I'm going to solve that for omega. And you get g tan theta all divided by A plus L sine theta. And that's all going to be under the square root. I have no idea how this relationship looks. I got a theta in two different places, and there's no way to bring them together. So, there's no way to make that simpler. There's nothing I can do about it. I will say that, because of the way theta is measured, it can be 0. That's when the system is still, right? That's when they're just straight down, and that is, when theta is 0, omega is 0. Theta can't be 90 degrees, though. You can't spin it fast enough for everybody to be perfectly flat out, right? Because tangent won't allow it. Tangent goes to infinity there. But you do have some other little interesting things here that clearly the faster if you want the people to swing outward more, you got to spin it faster. But it also tells us that if you're just watching this stupid ride, you could figure out how fast it's spinning by looking at the angle it's making. I guess. But, just to be honest with you, although that's true, you would also have to know this, the size of the ride. And I'm like, I don't know why they have us solve this for omega. It seems kind of ridiculous until you get to what the rest of the problem is about. So there's more to the problem. Determine the minimum work that the motor that powers the ride would have to perform to bring the system from rest to the constant rotating condition of figure 2, and express your answers only in those terms. This is where our rotational motion stuff comes into play. Once a system is moving, it has kinetic energy. And it's all rotational. We could deal with it as translational, but we already have omega. So we could say that the ride has all rotational kinetic energy, and it got that from rest. So we might want to say that the work done equals whatever the change in kinetic energy is. And that would seem like a pretty reasonable thing to do. We have the velocity. There are 6 people going around in a circle. So 6 times, I guess you could do 6 times 1/2 I omega squared if you want. But we don't have an expression for I. We do have an expression for omega. We could convert that to the linear velocity. It's the same amount of, I'm going to let you know this, it's the same amount of work. If you want to find I, it's not particularly hard to do so, and you can. This is just 6 point masses, but you wouldn't have A here. You'd have to have this A plus L sine theta. So I is just going to be 6m times A plus L sine theta, and that would be the moment of inertia of the system. That's fine, and that works great. You can plug that right in. Or you can do V equals omega times R, but remember, R is also this. So which one do you want to, this is all squared, squared. So which one of those do you want to do? You need to do one of these. So either you're going to do 6 times this. Well, I'm sorry, you wouldn't do 6 times that if I put the 6 here. So let me take that 6 away. Or you can use this and do 1/2 mv squared for each person, but then you would have to take this and use it to find v. I'm going to do this one. There's a couple reasons for it, but one, I spent all that time setting up what the moment of inertia was, so I want to do it that way. So come back to that. Get rid of all this extra garbage I don't need. Why won't some of this erase? There we go. There it goes. All right. And I get 1/2 times 6m A plus L sine theta quantity squared times omega squared, which is just all of this, G tan theta over A plus L sine theta. That's the kinetic energy. Now, some of this cancels out. Work done, sorry. Some of this cancels out, so I can do 1/2 of 6 is 3m, get rid of one of those and all of that, and I'll get A plus L sine theta times G tangent theta. And that's the work done. I'd say that's it, but it's not. Something's missing. And I tell you what's missing in the homework. They didn't tell you in the original FRQ. But if you did all of this, by the way, all of that ends up being like 6 points on this FRQ. It was a ton of work. But if you do all of that, that's what you get. But you're missing something. And what you're missing is there's now gravitational potential energy in the system that wasn't there before. All the occupants got lifted up a little bit. And you have to add that amount of potential energy to the work done. Because the work did two different things. It spun the ride up, but it also lifted all 6 people. So this part, I think, is subtle and non-intuitive. But you'd have to add 6 times mgh. And you'd have to figure out what h is, which we already have an expression for it. It's L times 1 minus cosine theta. And that's the work done. Crazy, I know. It's a crazy question. What's worse? Crazy question that was actually on the exam. So as crazy as it is, somebody thought it'd be okay to put it on an AP exam. Now this is an oldie. I mean, this one's really old. It doesn't quite predate me because none of them do, but it's pretty close. It's like 72 or 74. It's way old. It's back when they gave the answers that come with it, they're handwritten. So that tells you how old it is. All right. Did over here. This was the entire FRQ, every bit of it. So in doing this problem, moment of inertia first. And you construct it from the bars. If you did that, well, heck, you don't even need my class anymore. Get any college you want. All right, so that's moment of inertia. You have to work that out. The 2 squared is going to give you 4. 4 and a 12th is going to be 1/3. And 2 times that's going to be 2/3. So I believe this comes out to be 2/3 mr squared plus mr squared. I'm doing the math really fast in my head, but I think that works out right. You might want to do the math to make sure. But then you add those 2 things together, and that'll be 5/3 mr squared. And that has to be the moment of inertia of the ring. So you do that, which already is quite a bit. Now you've got a combination force and torque problem. We've done this problem already, so I don't want to spend too much time, but I'm going to call this side T2, and this side has T1. Those are the tensions. And since we've kind of done this problem, I'm going to kind of breeze through it as fast as I can so we can get to an end. I'm making this way positive, and this way positive. Is that all good for you guys? So we have the 2mg minus T2 equals 2ma. And that's the net force acting on this mass. That all good? And then I've got T1 minus mg equals ma. That's the force, net force acting on that mass. So I could bring these together, but we know that those 2 things, unfortunately, they're not enough. So because they're not enough, we're going to have to do more than that. So let's consider the net torque about the wheel. The net torque is going to be R T2 minus R T1 equals I alpha. And like I said, I would spend more time doing this, except we've actually done this exact same problem already. So I feel pretty confident that that's all okay. Is that all okay? Lots of things they have to do to make this work, but there's so many points here that they're probably giving you the lion's share of the points just for doing what we're talking about right now. If you want to get all the points, make sure that you do this substitution. That's all locked in together. This system moves all together as one. So movement of each of the individual masses is related to how fast the wheel spins. And when we do that and plug in our moment of inertia, 5/3 mr squared, all times a over r, the one thing that happens is, under this circumstance, all the r's cancel. Doesn't always happen, but in a problem like this one, where everything's in terms of r, and the problem was carefully crafted to be that way, the r's will often cancel, giving you T2 minus T1 equals 5/3 ma. We all good? All right, so that gives me a way to figure out the acceleration of the system. That's going to be subbing all of these things in. And when we sub them all in, 2mg minus mg equals 2ma plus ma plus 5/3 ma. So mg, another award. Yay. 3ma plus 5ma, 14/3 ma. I got a common denominator of 3. 3 times 3 is 9. 9 plus 5 is 14. I think that's right. And so cancel out the m's, and the acceleration is 3/14 g. Now, there's no particular reason to leave this in terms of a fraction. except that 3/14 is probably a non-terminating, non-repeating decimal. And 3/14 is easier to write because we're not done yet. To do the whole problem, we will need to figure out what T1 and T2 equal, because we're going to need that to figure out the normal force from the table. So T1 is MA Am I doing that right? No, plus mg. And T2 is there. Not fun. Yeah.
This is a random question because I was going to ask you yesterday, but I didn't.
If it's about this problem, I'll answer it. If it's not about this problem, I won't.
I'll just ask that.
Okay. But it's not about anything about this problem?
Well, it might. It depends on how the problem finishes.
All right, let's finish it then. Because we're close to the end. What I did was I solved this for... Whoops. I solved this for T1, which is MA plus MG. That's what I have here. I solved this for T2, which is going to be 2mg minus 2ma. 2mg minus 2ma. I need to get these all worked out. So this is 3/14 mg plus mg, which is going to be 17/14 mg. Boy, I think that's right. I hope that's right. And then this is 6/14 minus 28/14. So that's going to be 22/14 mg. And I really hope somebody's checking my math on this, but I think I'm pretty sharp. I think I'm pretty okay with the arithmetic. Whew, that's a lot. So now let's do the whole problem. What is acting downwards on the system? Well, it's 2m and m aren't really parts of the system. I've got T1, T2, and they act down. And let's see, the weight of the wheel is, what's the weight of the wheel? 4 mg. That's the weight of the wheel. Yep, that's the weight of the wheel. And then there's also 5 mg, the mass of the stand. And then normal force up. So we add all that together to figure out what the normal force is. So normal force equals 5 mg plus 4 mg plus T1 plus T2. Or 5 mg plus 4 mg plus 17/14 mg plus 22/14 mg. 9 mg plus, holy crap, do we have to do that? 39/14? Huh? 165/14? Isn't it 22 plus 17?
No, I'm saying wasn't that I
It-
know it was right, so just I did it.
All right. So, yay? The real question is 165 divided by 14 less than 12? Because this whole thing was predicated on the whole fact that the whole thing was 12 mg. What is 165 divided by 14? What is it? 11 point. So, yes, it is slightly less than 12 mg. Boy, that's a long way to go to get there, isn't it? This was an AP question. I mean, the only difference between this AP question and what I gave you for homework is you had to construct the moment of inertia. In the actual AP question, it was just a disk. I'm just saying these are the things that have been on the AP exam. So, they're exhausting. This one is really an exhausting question. So we've looked at two of them. The talking time for this problem was 11 minutes. Yes, ma'am. This is the entire FRQ. This is every piece of it. So it had a net force problem. It had and they gave parts. So you had to find the acceleration of the system. So it was broken down. But the last thing was you having to find the normal force in the table. But this was the entire FRQ, just like okay, moment of inertia of a thick ring. That's what the problem asks?
Yeah.
Okay. So I will, let's start by having a ring. This is part of this is a calculus problem, and part of this is a physics problem, when it involves setting it up. I try to separate out the part that's really the physics from the part that's the calculus. The integration is the calculus, but setting up the sum, that's physics. Although I think what we miss by having two distinct and separate classes is the fact that the modern conception of physics was developed with calculus at the same time. So when I indicate that, the creating the sum is the physics part, and then the calculus is just doing the integral, that really is not true. That's kind of me taking liberty with the concept, but they're not going to teach you in calculus how to set up the sum. That's the problem. Now, we've arguably done this problem already before, so I don't have to do all the pieces. So I feel like I can go a little bit quickly through it. And I say that knowing that if you've never done this or if you've not acclimated, spent some time thinking about it, then it's going to be just as confusing this time as the last time. But where do we start? We start by making a piece of mass, a square. This is an area. And because it's an area, I want to do a little bit of prep work before I get started. It's a thick ring of mass M. And inner radius, I probably said Ri. And outer radius, Ro. If I have a disk, I want a disk. If I have two disks, fill, there. Disk number 1 and disk number 2. And this disk has radius Ri, and this disk has radius Ro. And I know from definition then that this has a moment of inertia of 1/2 mRi squared, and this has moment of inertia 1/2 mRo squared. Why can't I just subtract those two to get the moment of inertia of the system? First, moment of inertia is add together. There's no negative moment of inertia, so that's the first reason why this won't work. But the second reason why this won't work exactly as stated is the m's aren't the same, right? If it's a uniform density, if the two things are made out of the same stuff, this m is more than this m. You'd have to find, I would assume, that if you wanted this to work, you would have to find out the value for m that you'd have to use for each of them in terms of the other. Like how much? So what you would end up probably getting is the same answer we got, because you'd end up getting masses that have ratios in them for the radii. And that would probably work out and end up to get the same thing. I assume. I've never done it that way, so I don't know. And I'm just not really interested in trying because, that's contrite. So I guess it might be interesting to figure that out. You had like this. Right. I mean, if I want to find a moment of inertia of this system, well, do I want to do the summation or just grab the moment of inertia of the whole big rectangle and subtract a piece of it? Well, I don't know. I don't know if it would work or not. Something to interesting experiment with. Can you subtract a moment of inertia? Now, I do know the answer to this. It's just that none of this really matters in this class. And what you can find is you can do this in any number of ways you want. You can break this up however you want. The summation is a sum. So you can break this into any organized way in which you wanted to break it up and add it all up to get the moment of inertia. No one way happens to be better or worse than the other. You could break this into two sections that are divided by based on the idea that you've got something like that, right? This part and this part you could treat as one section. They're a continuous bar. And then this is a continuous bar. And this is just a point mass far away from the axis of rotation, assuming this is the axis of rotation. I don't know. I'm just trying to make this up. So, all right. I am desperate for you to be able to do this problem. It has been on the AP exam. It is hard, I think. So I'm going to try and draw this out so that it has a little bit of purpose. And it's obvious. So I'll do the ring. Is that okay? That way you guys can do the disc or the sphere or whatever. This object is not spinning. It has an initial velocity in this direction, but its angular speed is currently 0. Everybody okay so far? It's a ring of radius r, mass m. There is a coefficient of kinetic friction of mu k and a coefficient of static friction of mu s on a surface that the ring is about to encounter. The ring, when it encounters this surface, is going to experience a frictional force that's going to cause it to change its velocities. And eventually, over time, the ring will go from sliding and no rotation to rolling. And we'll just call this V final and omega final. So it's going to go from a state of having no rotational speed and an initial velocity to a final state where the final velocity is going to equal the angular velocity times r. That is the final state of the problem. I think it's important that we start the problem with that in mind. And I think it's also important that you be thoughtful about what has to happen here. It's not as complicated as it seems if you understand what's happening. If you don't understand what's happening, then you'll never solve this problem. But there are two accelerations acting in this system, one positive and one negative. This number, is it going to get bigger or smaller when it hits the patch that has friction? Smaller. It's going to slow down. Everybody follow that? That's pretty straightforward. Why? Well, because net force is going to equal ma. And I'm pretty sure if I make this the positive direction, you need to be careful here from the very beginning. If I make that the positive direction, the moment the ring hits the area that has friction, it will experience a force right there that's in this direction. And moreover, that will be kinetic friction. It's sliding with respect to the surface, so it's kinetic friction, which has to equal ma. Now, the kinetic friction is something we know how to deal with. Kinetic friction is mu times the normal force. And on a level surface, kinetic friction is going to be mu mg. So that tells me from the very beginning that my acceleration is going to be equal to minus mu kg. Just substitution. And it is expressly negative. This acceleration is expressly negative. I was careful to set this whole thing up to ensure something's happening. This thing's breaking. I think my huge bulk is finally just having a problem. I lean into it the whole time, and I just think that that's bad for me. I think it's going to have a problem. One day I'm going to be doing this, and all of this crap is just going to go flying that way. I just want you to, you might be here for it. And if you are, awesome. Get video, because it'll probably be my last day of instruction, because I'll spill hot coffee all down the front of me. Okay. At the same time, this frictional force causes a positive torque. Right? If you look at where that frictional force is, it's going to cause the wheel to rotate in that direction. I can right-hand rule it, but that's going to be a positive torque based on the direction that I said is positive. So net torque is going to be equal to I alpha. I mean, we could do this all in terms of I. And if we do, then at the end of this problem, you could just plug in moment of inertia of the ring and then solid sphere. That would be helpful. I'm not going to do it that way because I want you to have, but you could work the problem right now in just terms of I, and then you would have it. You'd have the answers to both your homework questions. Smart kids like you guys could do it that way. I am feeble, so I'm going to put in the things that are easy. I noticed right away that my frictional force causes this torque, and that if it's a ring, it's mr squared alpha. You might be compelled to put in a over r here, but you would be wrong. It's not rolling yet. The angular acceleration is not related to the linear acceleration. So you need to leave it as just alpha. It's slipping. This is still going to be mu k mg mr squared alpha. I'm going to solve this for alpha. And canceling the m's, and I can cancel one of the r's, I get mu k mg over r. All right, so I have two accelerations. I have this acceleration, and I have this acceleration. Your problem asks you to figure out how far does this wheel go until it's rolling. You want this distance. Yeah.
Would there be an N?
Would there be a what?
An N for rotational acceleration? Because when the N's divide and
Oh, looks like they'd cancel out. Okay. There. Yay. Now, what you have to do next is understand the things that are related and the things that aren't. This acceleration is a constant. This one right here. This acceleration is a constant. So, knowing that they're constant means I can use motion equations if I want. I have to figure out how far the wheel goes until it's rolling. Here's the thing. To be rolling, that has to be true. Right? I'm starting with this velocity, and I'm slowing down. And I'm starting with no angular velocity, and it's speeding up. To figure out how far the wheel travels while this happens is to understand that rolling begins when this equals this at the same time. So if I can figure how long it takes for the wheel to slow its linear velocity and how long it takes for the wheel to increase its angular velocity, they have to reach that point where they're related at the same time. So the goal here should be to figure out when that occurs. Follow what I'm saying? That's what you want to do. You want to figure out when they reach that united velocity at the same time, and then go back and figure out what the horizontal distance is. So, I'm sorry, let me say it again. Your question is, will the acceleration change when we go from slipping to rolling? First, I want you to understand that the type of friction changes. So I made that clear, but I'm re-instigating it because I want to hit record. The type of friction goes from kinetic to static. But once it's rolling, and this condition is the final condition of the problem, there won't be a change in the velocity. When I reach the condition for rolling to take place, then the friction no longer imparts a torque that causes a change in the angular acceleration, in the angular velocity. At that instant that I'm rolling, believe it or not, static friction on this surface will drop to 0, and I'll just be under the condition of rolling. I know it doesn't make a whole lot of sense right now because I'm having to explain it fast and a bell's about to ring, but work the problem out and find the final velocity, which we can do real quick, and then find the point where how far it travels. That's pretty easy too. And if you don't know what you're supposed to do, multiply both sides of this by r, and then set these two things equal to each other to get t by itself. Okay, you have expressions for a here, expressions for alpha there. Use that to solve for t. And then use probably this to find out delta x. Actually, you can use any function you want to find out delta x. Just pick one. And then we'll talk about the static friction tomorrow when we go over homework.